part 2 of B-1. I think I'll do 5 questions and then save the last 5 multiple choice questions for another video. So that puts us at number 41. A 5 kilogram box is sliding across a level floor. The box is acted upon by a force of 27 newtons east and a frictional force of 17 newtons west. What is the magnitude of the acceleration of the box? Here's our box, 5 kilograms. There is a force east, there is a force west. Let's see here. Okay, so what I really want, there's just a picture representation. What I really should be doing is drawing a free body diagram for this. And yes, it is a multiple choice, and no one's going to look at this. But it's good to get into the habit of always, doing the same things to figure out the problem. Okay, it's when you start skipping steps that mistakes get made. So it's a box. We really don't need the force in the y direction, but I will include them anyways. We do have a force of gravity downward. We have a normal force upward. Those are balanced. That's the last time I'm going to talk about them. We have a force of 27 newtons east. It just says the box is acted upon by this force. I'm just going to call this F. And the force to the west is a frictional force. It's somewhat less. I'm going to call this FF. Now, once we've got our free body diagram drawn, the next thing that we have to do is write out a net force equation. Again, I'm just concerned about the x direction here. We already know, or we should know, the box is not accelerating up or down at this point. My net force equation will look like this. F net x equals F minus FF. Force to the east, or the applied force, or whatever the force is in this case, minus the force of friction. Remember what Newton's second law says, F net equals ma. I'm going to tag on an x to remind us that we're dealing with the x direction here. Now we just have to plug our numbers in. We've got our diagram, we've got our net force equation, now we solve. The force is 27 newtons to the east. We did kind of coincidentally pick east to be our positive direction. Force of friction is 17 newtons. It is negative, or we put a minus sign in front of it, because that is in the opposite direction, the direction opposite that which we called positive. The mass is 5 kilograms. Looking for the acceleration. 27 minus 17 is 10, equals 5 ax. Divide both sides by 5. We end up with an acceleration of 2 meters per second squared equals ax. That would be choice number 2. And it is positive, meaning that the acceleration is in the direction of the net force, which means it is in the direction of the biggest force. There's 41. Question number 42. Diagram below represents a 2 kilogram toy car moving at a constant speed of 3 meters per second, counterclockwise in a circular path with a radius of 2 meters. At the instant shown in the diagram, the centripetal force acting on the car is what? Okay, so centripetal force, that's what we're looking for. It looks like we're looking for the amount, the magnitude of the centripetal force. Now, we should know a couple things. We can eliminate some answers before we even do any calculations. The car right now is moving counterclockwise around this loop. That means that at this instant, the car is moving, I guess this would be north. The car is moving in this direction. Don't say the car is moving in this direction. That's not really a direction, that's a curve. Which way is the car moving right now? It's moving north. The velocity, and that was very crooked, the velocity is to the north. So, it's moving that way. Why does it follow the curved path? It's because the acceleration and the net force point in towards the center. FC and AC point towards the center to allow the car to move in a circular path. So that means the centripetal force must point to the west. If it says to the north, those cannot possibly be the right answers. Get rid of those. So we're down to either 4.5 newtons west or 9 newtons to the west. Now we can actually calculate our answer. We know that the centripetal force, centripetal is just a fancy word for net. So we can rewrite Newton's second law in terms of centripetal forces and accelerations. Instead of writing F net equals ma, we write Fc, the centripetal force, is equal to the mass times the centripetal acceleration. We also know an equation for centripetal acceleration right from the reference tables. It is v squared over r. I'm going to take this equation and plug it in here so I can get one big combined equation. The centripetal force is equal to m times v squared over r. Or if you want, just combine it all into one fraction. mv squared over r. Now we are told, now we are told the mass, 2 kilograms. We are told the speed, 3 meters per second. We are told the radius, 2 meters. Let's plug all those in. 2 kilograms times 3 meters per second squared over 2 meters. I'm going to do some math real quick. I've got a 2 on top, 2 on the bottom. Those are going to cancel out. 3 squared is 9. So we are looking at choice number 4 in this case. Okay, here's question number 42. Nice electricity question. Very good question, actually. In which electric circuit would the voltmeter read 10 volts? This is a very interesting question. It's getting at not only what type of circuits are these, but what does a voltmeter actually do? How does it work? Okay. So let's first start by analyzing what type of circuit everything is. We know two basic types of circuits, a series circuit and a parallel circuit. In AP, we can combine those two. The Regents tends to stay away from that, and I will as well. So this the first choice, the first circuit here, we have two distinct paths that current, in other words, a flow of charges, could go around as it makes its way around the circuit. It could go through this first resistor, or the top resistor. It could go through the bottom resistor. There are two distinct paths. That means that this is a parallel circuit, so I'm just going to put P next to it. All these other ones have one path for the current to go through, okay? The voltmeter doesn't constitute another path, really. It's something that the circuit would be complete even if we didn't have the voltmeter there. So we don't need it. Remember, a voltmeter is there to measure voltage, or really to measure potential difference. Those two things mean the same thing. Well, get in the habit of saying potential difference. It sounds a little bit better. So it's in there to measure potential difference. It's not necessary for the circuit, okay? It's there to measure V. There is one path for each of these. These are all series, so I'm just going to put an S above it. Now there are different rules for parallel and series circuits. Let's start with the parallel circuit, okay? If our battery has a voltage of 20 volts, a potential difference across a battery of 20 volts, that means that the voltage, I guess you could say, goes up as you go from one side of the battery to the other. So let's say we start over here, some charges move through the battery, they start over here, let's say at 0 volts, they go through the battery, now they have 20 volts, okay? Now they're at a potential difference of, or they're at a 20, I'm working on how to say it, they gain, there's a potential difference of 20 volts here. It's an increase, okay, in voltage of 20 volts. As they go through the circuit, they must lose the 20 volts, okay? That 20 volts of potential difference must be used up somehow. Because what voltage really represents is the energy per charge, okay? So think of it this way. The battery gives the charges some energy. They better lose the energy by the time they get back to where they started, because otherwise you would just have all this energy building up and building up and building up, and it would cause an explosion, melt the circuit, or something like that. The battery gives the energy, it gets dissipated somewhere else, and the total voltage gain of the battery must equal the total voltage drop across a path. So since we have two paths, the voltage drop for each path has to be the same. That's the other thing. You can't have two different voltages at the same spot. The voltage drop for the 1 ohm resistors must be exactly the same, and because there's only one resistor in each branch, what that means is the voltage gain in the battery must be equal to the voltage drop of either resistor. Either of these resistors has to have a voltage drop of 20. So that would mean that this voltmeter reads a drop of 20 volts. We want a voltmeter that reads 10 volts. That doesn't work. Now let's look at this series circuit. Look where the voltmeter is placed. It's placed around the entire, it's around both resistors, okay? So really, it's the entire voltage drop here. Again, we have a voltage gain of 20 volts. The entire voltage drop should also be 20 volts, since we got both resistors here inside of our leads to the voltmeter. That's not going to work either. Now we go down here. Now you might say, you look at this and you say, we have it around just one of them. Both these resistors should have the same voltage drop. They should be places where energy is being given up when the voltage decreases. So if before it was 20 volts, you put it on one, that should be 10. But take a look at your battery. It's only 10 volt battery now. So then this voltmeter actually has a voltage drop of only 5 volts. That doesn't work. The answer is choice 4. Put the voltmeter around both resistors in a simple series circuit like this that has a battery voltage of 10 volts. The entire voltage drop will be 10 volts. That is choice 4. Okay. Question number 44. Back to the reference tables to the modern physics section. The lambda baryon has a quark composition, UDS. Which particle has the same electric charge as the lambda baryon? So what we need to do is we need to figure out what the heck UDS means. We go to page 3 on the reference tables. And we see that UDS corresponds to an up, a down, and a strange. Okay, up, down, strange. Up has a charge of positive 2/3 E. Down has a charge of negative 1/3. Same does strange. Okay, quarks can have fractional charges. That is no problem whatsoever. Okay, so UDS, let's see, the charge of that entire thing would then be positive 2/3 minus 1/3 minus 1/3. You have 2/3. You take away 1/3, you're left with 1/3. You take away another third, you're left with a 0. Which particle, so 0 E, I'll put E's there. Which particle has the same electric charge as the lambda baryon? Which one has a charge of 0 or is neutral? Should be kind of obvious. It's a neutron. Very simple if you know how to read that chart. Okay, very, very simple. It's not an electron that has, all of these things have charges. Okay, none of those are neutral. Last question for this video. How many kilograms of matter would have to be converted into energy to produce 24 megajoules of energy? Okay, we're converting matter into energy. That tells us that we need either a conversion between electron volts and universal mass units, which it doesn't really say anything about those. We got megajoules, but we'll convert that in a second. Or we need Einstein's famous equation, E equals mc squared. Okay, we're looking for mass. Okay, we're looking for kilograms. The only tricky thing here is it says 24 megajoules. Okay, you might be thinking, what the heck is a megajoule? Let's go to the front. Mega has the prefix, of course I've probably written right over it. Mega has the prefix, is the symbol capital M. Notation is 10 to the 6th. So that means that anytime you see the word mega in front of something, you could replace it like this. 24 times 10 to the 6th joules. Now, of course, it's not standard scientific notation, but who cares, okay? If you wanted it to be standard, you would just put this as 2.4 times 10 to the 7th joules. But it doesn't really matter, okay? We can plug in, calculators can deal with 24 times 10 to the 6th, absolutely no problem. We plug that in for the energy. 24 times 10 to the 6th joules equals M. And please remember that C is squared in this equation. 3 times 10 to the 8th meters per second. I almost forgot right there. It's squared. And it works out that the mass is equal to 2.67 times 10 to the negative 10 kilograms, which conveniently is choice number 2. Okay, we'll be back in a little bit with the last video. Bye.